Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. Today we will continue and finish actually the relational model. I don't really have that much to tell you, additionally to last week. And then we will go to a practical lecture where we will discover how to actually do this with SQL and PostgreSQL. So before we continue, I have two questions for you that I'd like to ask you on the Clicker app. Which is right here. So this is the first question, which is what kind of integrity constraints on a relational table have we not covered? Here are 4 of them, and there are 3 of them that we did cover, and 1 of them we didn't, because that doesn't make sense. So I'm asking you to pick the one that is incorrect among the 3. So is it relational integrity, atomic integrity, attribute integrity, or domain integrity? Your answers. We have a majority for attribute integrity. Indeed, this is the only one that I didn't talk about. It doesn't really make sense, right? Why would you constrain the length of the attribute names? And here is another one. What is a relational table? It's kind of where we stopped last time, right? Multiple answers are possible in here. So is it a mathematical relation over attribute domains? Is it a mathematical relation over several sets of attributes? Is it a set of relations between strings and values with monotonous support? Or is it a set of maps from strings to values that additionally fulfills relational, atomic, and domain integrity? This is what kept us busy last week, right? We spent almost the entire time trying to define what a relational table is. Let's look at your answers, multiple possible. And we have almost. So these were the correct ones. It's the relation is about the attribute domains. Remember that the relation, that's a subset of the Cartesian product, and the Cartesian product we take over domains. If you had a relation over sets of attributes, you would have tuples that contain attributes, but we don't want the attributes in the table. We want the actual values, right, from the domains. All right, so these are the 2. So the first one is the one you commonly find in textbooks, and the fourth one is the one that is forward compatible to big data, and that is also mathematically closer to what a relational table is. All right, now I'm going to come back to the slides, and we'll finish first what we did last week. All right. So we stopped here. So the first definition, we covered the relations over domains. But my second definition was that a collection is a set of records, and these records are actually mapped. Every record maps an attributes to values, right? So we have a first record. Last is mapped to Einstein, first is mapped to Albert, physicist to True, and year to 1905. So you see these are maps from strings to values. And in that case, we have 3 maps, 3 records, right? So we have here a collection that is a set of maps, a set of records, right? 1, 2, 3. And again, here I map last to Turing, first to Alan, physicist to False, year to 1936. All the other strings in that map are not mapped to anything. Only these 4 strings are mapped. For whom is that clear? For whom is that not clear? Okay, so it's a set of records, and mathematically, the records are just maps or partial functions. Now, if I define my collection as a set of maps in this way, this is also a collection, because I didn't require anything about the maps, right? I'm just saying these are maps. So the first map has maps for strings. The second map is mapping 3 of them, last, first, and physics, to values. And the third map in blue is mapping last, first, year, and theory. So technically, if you just say it's a set of maps, you can have a mess, right? So we need additional constraints. And these constraints are known to you. These are the ones we covered. The first constraint is relational integrity. We can request that on top of the definition, meaning all of the maps must have exactly the same attributes, exactly the same support. So here we have every time last, first, physicist, and year. And because we have that, we don't need to repeat the headers, right? We can just merge that, right, in a single table. So this is what we get if we have relational integrity. The second constraint is the atomic integrity. It's just asking that all of the values that are in the maps, all of these values must be atomic. And we'll discover today a lot of atomic types, but there cannot be nested tables. That's not okay. You cannot map an attribute to a nested table. That doesn't work. That's the second constraint. And the third constraint is that I'm able, in the columns, so basically if I take a specific attribute, a specific string, everything that is in that column, that must belong to some type. I must be able to figure out some type that it belongs to. In the first column, these are strings. In the second one, these are strings. In the third one, these are Booleans. In the fourth one, these are integers, right? So that's domain integrity. And typically, I can add here this yellow band right below my header, my attributes, that basically gives me the domains, the types, right? Domain and type, I can use interchangeably. Right. Okay. So if I want to define that mathematically, it looks scary. It's actually not, because this is really just what I said here. It just says that for every one of these attributes that you have here, you map it to some domain. And then whenever a tuple has some value, it must belong to the domain that is specified here. So it means that if I take false here, it must belong to the domain Boolean, and I have to be able to put these domains in such a way here that every column belongs to the domain mentioned here. All right, so that's another example that each one of them here, it says string. So each one of the values here are actually strings. This doesn't work here. This wouldn't have domain integrity. I could try to say, okay, this looks like integer. I could try that, but it doesn't work, because here you see I have this E that is not an integer, right? So it doesn't fit in there. And here we do not have domain integrity. I have basically a string E and integers. There is no way you can find some domain that unifies that. Mathematically, you could take the union of the set of strings and the set of integers, but it doesn't make sense in terms of databases, right? You really have some type that belongs to a specific list that we'll discover today. So what does it mean for our 3 rules? They are not enforced by the definition of the collection as a set of map. I have to add on top of that definition these 3 constraints, constraining the attributes, the supports, and the set of values. And this is my relational table. It's basically a collection, so a set of maps that also has relational domain and atomic integrity, right? So this is it. That's my definition. A relational table is a set of maps that I call records that has relational domain and atomic integrity. Now, I told you last time that there are people who like to slightly alter the semantics here and say, if we want to allow repetition of maps, I want to allow for some map to occur multiple times, for some records to occur multiple times. This is fine. Then I just define my collection as a bag of maps. You remember that with bags, we allow multiple occurrences. So in that case, you see this map, last Einstein, first Albert, physicist, true, year 1905. It appears twice, right? In the first and third position on the screen. So technically, that's a bag of map, all right? Here and here, it's the same one. In a set of map, you could not have that. Note that in a bag of maps, the order is irrelevant. I care about how many times they appear, but there is no particular order. I could shuffle that around and that would still work. So then I also add my 3 constraints on top. I would also require relational integrity, domain integrity, and atomic integrity. And then I would get a relational table with the bag semantics. Yes, we have a question. Oh, it's just the map. It's a map from strings to values. A map. So technically, it's a partial function mathematically. Yes, if you don't have exactly, if you don't have the cross, that would force you to map every string to a value. But that doesn't make sense, right? We only want to map, in that case, 4 strings, right? So the cross allows you to map just a few of them and not all of them, right? That's what it means. It's a partial function, but the computer scientists, they call this a map, right? It's also easier to say, right? A set of maps. Make sense? Okay. But don't worry too much. The notation is there, for whoever, it basically makes things formal. But really, what's important is that you understand the ideas and the concepts in there, right? And what is, if you want, since you asked the question, let me explain why I put this formula here. This here is a function that associates every map with an integer. Every map is associated with an integer. So this map here is associated with what value? 2, because it's twice in there. This map is associated with value 1. And every other map, there is no cross in here, right? So I have to associate every map. Every other map is associated with how many occurrences? 0, right? Exactly, 0. So 0 for all the maps, except this one that is associated to 2, and this one to 1. So this is really associating every possible map you could ever imagine to the number of times it appears in the bag. So that's just my notation for bags. And then I have lists. And a list just means that not only do I allow multiple occurrences, but on top of that, I even allow an order. So there is really a first record and a second record and a third record and a fourth record. So the order is important here. So I could also take this semantics, take a list semantics. This awful thing that is on the top, the formula, it just says that you take some n and then you map each one of the integers from 1 to n to some map. But that's just the way of telling the order, right? So 1 is associated with this Albert Einstein, 2 to Alan Turing, and 3 to Kurt Gödel. All right? But again, don't be too much scared by these formulas on the top. This is really just to make it formal. But what you need to understand is that we have a collection as a set of records, or a list of record, or a bag of record, and that's something we can choose. It's really a choice of semantics. And the records are just maps from strings to values, and that's it. Yes? Yes, in a list, you allow for repetition. Yes, because the integer on the left is not part of the tuple. It's only here to give you the order, but it's not actually part of the record. So that would be technically exactly the same one. It would just be both in the first and in the fourth position. Yeah? Okay. All right. And then, of course, I can do exactly the same as I did for sets and bags. Also for lists, I can also require that I have relational domain and atomic integrity. And then we have a relational table, but this time with lists semantics. We'll see in practice that all of the modern SQL database systems, including PostgreSQL, they support lists. So you will be able to have an order in your relational tables. Sometimes the order is a bit random if you didn't specify it, and then it kind of feels more like a bag, even though technically there's still an order. But you'll see when you start using it, how it works. And the sets of maps, this is really like the original definitions where it all started. The theory technically has a set semantics, right? But really, in practice, it's so convenient to have an order, and that this is what people do. But I just want to know that there are the 3 ways of doing that, and the 3 ways are okay. And what we have then in practice, and this is also the way we teach it to computer scientists, is that when you have the intent to define a table and put data in there, it all starts with a schema where you specify the name of the table, scientists, and then you specify your attributes, because we have relational integrity, so it's always the same attribute in all records. And here we have PID last, first, and country, PID last, first, and country, and then you indicate the type or the domain that you want. So PID is an integer, string is last is a string, first is a string, and country is a string, right? PID means, in that case, person ID. It's something we love to do in databases. Whenever we have records in a database, we say the first letter of it, ID. So PID is a person ID. If you have course IDs at ETH, that would be CID. If you have the room IDs, that's RID, and so on and so on. So whenever you see these 3 letters that look like that, it's very probably just some ID to identify the records. And the first letter is just the initial of what we have in the table. Okay, and that we'll implement in SQL today, right? So now, if you really want to formally specify, for example, this table right there that has 1, 2, 3, 6 records, then you could explicitly give the maps mathematically. So technically, you would have, you see the first map that associates, if I use my mathematical notation, customer ID maps to 1, security ID maps to this, and quantity maps to this. This is my first map. And this is a set. I use the curly braces. So it's a set of these maps when I write my maps here in extensional form. And it belongs to the set of maps from strings to values, right? Every one of these 6 is a map from strings to values. So that set of maps is a subset of the set of all maps. Make sense? Are you following? Okay. And just for the notation, it's kind of convenient, especially in database design theory in a few weeks, we might give names to the records, to the tuples. So if we call that record T because of tuple, so tuple record is all the same thing, that's just the synonyms. So if I call that record T, then I can use the dot notation with T.customer ID, that's actually 1, T.security ID, that's this. If you do object-oriented programming, who knows Java, all these languages? So you should be familiar with the dot, right? It shouldn't surprise you too much, right? In fact, this is how we connect to object-oriented programming. But we can also use subscripts, which is just another way of doing that. That sort of notation is really convenient to demonstrate theorems in the database design theory when we will dive into this, right? Okay, but of course, all this here, we never do that. The database people, they will never write a maps like this. This is just like the math, the formalism for it that there is behind. But the database people, they like to draw things like this and maybe use this notation right here, but that's pretty much it, right? So we have every time a header, and then the extension, that's just what we call all the records. And this stops the relational model lecture. So are there any questions before we move on? Yes? Oh, the update didn't work. That's because last week I just decided to redo all the slides because I wasn't satisfied. I wanted to improve the pedagogy. And if it's not up to date, it means something went wrong with the uploads. So I will check to make sure that the new version is uploaded. Yeah, so it's Polybox, so sometimes it doesn't connect fine. Yeah, thank you very much for letting me know. I will do that. Yeah, I really, it's important to me. I mean, I could just have designed the slides in the first year and then go like this for 20 years with the same slides, but I really don't want to do that. And every year, I mean, I see what works, what doesn't work, and I try to improve the way and the order in which I tell you things, right? Okay, any other questions? Who understands what a relational table is? Okay, awesome. Now, let's go to practice and let's go to PostgreSQL. So I'll interrupt the recording and I'll see you on the other side.